In this video, we're going to start examining the output of a nonlinear amplifier driven by a cosine a little bit more closely. We're going to do that by applying some trigonometry to the squared term in the amplifier's behavior, which is referred to as the second-order distortion term. We need to simplify this cosine squared term, but no one remembers trig identities, so we're going to use Euler's formula to think about complex exponentials instead. Once we've converted our cosine into an Euler representation, we can square it pretty easily in order to find this polynomial containing e to the 2jx and e to the minus 2jx. Those two complex exponentials can be combined back into a cosine in the final step of our derivation, which leaves us with a simple expression that doesn't involve high powers of cosines. So cosine squared of x is equal to 1/2 times 1 plus cos 2x. Finally, we substitute that identity back into our v out of t expression for a nonlinear amplifier. This equation has some terms that are a bit surprising. First, the cosine squared creates a DC term, so putting a high-frequency wave into our second-order harmonic distortion causes a DC shift in the output of our amplifier. This can be a big problem for some amplifiers because it messes with their operation. However, it's common to fix this behavior by putting a capacitor in series with the amplifier, a practice called AC coupling. The second term in this equation creates a frequency component at twice the input frequency, which is referred to as the second harmonic. Harmonics are signals that have frequencies that are multiples of some lower frequency, which is called a fundamental. This is very different from linear systems, which always have output sinusoids at the same frequency as the input frequency. Our nonlinear system is now producing an output sinusoid at double our input frequency in addition to the input frequency. We can make a quick picture of this, which shows that our amplifier's output spectrum has the expected linear gain at the input frequency omega, and another component at 2 omega, and a small DC offset. This plot is in units of power, which is a common way to draw spectra for RF systems where we're more concerned about power gain than voltage gain. As a reminder, we convert from our 0 to peak amplitude to power by squaring the voltage amplitude and dividing by twice the resistance it sees, which is probably Z0 if it's matched to the surrounding RF system. This graph is a great summary of what's going on, but we can come up with some concise numerical summaries too. First, it's common to describe the power of the second harmonic in relation to the power of the fundamental signal. We do that by using yet another funny decibel unit called dBc, or decibels relative to the carrier. We'll talk about where the term carrier comes from in a later video, but for now just remember that it refers to the fundamental. Equality in dBc is 10 times the log of the thing we're measuring, divided by the power of the fundamental. So when we say that the second harmonic is some number of dBc below the fundamental frequency, we're effectively measuring this vertical height in decibels, because we're taking the ratio of the second harmonic power to the fundamental power. Finally, HD2 is a specific measure of the size of the second harmonic relative to the input. It's the voltage amplitude of the second harmonic divided by the fundamental frequency voltage amplitude. And the expression you get when dividing those two coefficients, so just taking the ratio of this coefficient and this coefficient, is written down here. You'll notice that HD2 gets linearly larger as VZP increases, so the second harmonic grows linearly relative to the fundamental, or it grows quadratically and the fundamental grows linearly. So in summary, the second-order distortion term creates a DC offset and a harmonic at 2 omega. The DC offset can be problematic in some designs, but sometimes you can get around that with AC coupling. The harmonic can be measured relative to something called a carrier, or a fundamental, in units called decibels relative to the carrier, and an expression for calculating decibels relative to the carrier is here. And the second harmonic can also be measured using the HD2 quantity, which is defined here.